Renewable energies have been gradually increasing their rate of market, with a rapid and sustained growth from 2006 to 2011. Photovoltaic solar energy has grown more quickly than other renewable energy sources during this period, with an average annual growth rate of 58%. The spectacular growth of the photovoltaic power installed in recent years has surpassed all expectations, even the most optimistic, demonstrating the potential of this technology as a source of energy in the world. At the end of 2011, accumulated world capacity stood around 70,000 megawatts, mostly being grid-connected installations. The world production of cells has also followed a constant evolution at the same time as new thin-film technologies have been incorporated into the market. Such rapid growth led to the development of new markets, up to a point that, according to the data for 2011, there is now a predominance of the Asian market in the manufacture of cells, especially from China. In this context of intense development, Latin America and Caribbean countries have huge potential, many of them being located in the so-called Sun Belt, or area of the planet with greater amounts of solar radiation. The photovoltaic effect is the direct conversion of sunlight into electricity. The element that makes this possible is the solar cell, which in its more conventional structure consists of a semiconductor of silicon doped with boron and phosphorus. It is prepared in such a way that the amount of radiation inciding on the surface is maximized, and the power generated can be extracted to an external circuit. The main elements of the solar cell are the semiconductor active layers, the emitter or N layer, and the base or P layer. We also have the anti-reflecting coating, the metallization grid, and the metallic back contacts. The fundamental solar cell descriptor is its current voltage, or IV, characteristic, which represents all possible combinations of voltage and current that can be drawn from a cell under certain conditions. The main elements that emerge from the current voltage characteristic are as follows. Short circuit current, ISC. This is the maximum current that the device will produce under defined conditions of lighting and temperature, corresponding to a zero voltage. Open circuit voltage, VOC. This is the maximum voltage of the device under certain conditions of light and temperature, corresponding to a current equal to zero. Maximum power, or Pmax. This refers to the maximum power that the device will produce under certain conditions of light and temperature, corresponding to the maximum product of voltage times current. Current at maximum power point, Imax. This is the current value at the maximum power point in certain conditions of light and temperature. Voltage at maximum power point, Vmax. This is the value of voltage to the maximum power point in certain light and temperature conditions. Fill factor, FF. This is the value corresponding to the ratio between the maximum power point and the product of the short circuit current times the open circuit voltage. Efficiency. This is the ratio between the power that the cell can deliver and the power of the solar radiation falling on it. There are various types of photovoltaic cells depending on the material they are made of or the structure of the cell. So we have monocrystalline silicon solar cells, polycrystalline silicon solar cells, amorphous silicon solar cells. Then there are cells of hybrid materials, binary compound cells, and cells of ternary compounds. The term photovoltaic generator refers to the set of photovoltaic modules that provide power to a facility. The fundamental unit of photovoltaic conversion is the solar cell. In the first instance, cells come together in series or parallel to form the photovoltaic module, which is the longer commercial photovoltaic device prepared for operation outdoors. In real applications, photovoltaic modules are also joined in series and/or in parallel to constitute the photovoltaic array or photovoltaic generator from the installation. The conventional structure of the photovoltaic module consists of the following elements. Front cover. This should have a high transmission capacity in the range of wavelengths that can be used by a photovoltaic solar cell, from 350 to 1200 nanometers in the case of silicon solar cells. It should also have a low front surface reflection to capture most of the incident solar energy. In addition, the material must be impermeable to water with a good resistance to impact. It must be stable against prolonged exposure to ultraviolet radiation and must have a low thermal resistance. If water entered the interior of the module, this would corrode the metal contacts, causing a dramatic reduction in the lifetime of the module. In most modules, the front surface is used to provide rigidity and mechanical toughness. Among the materials most widely used to make the front surface are acrylic materials, polymers, and glass. The one most widely used tends to be tempered glass with a low iron content because of its low cost, high transparency and stability, impermeability to water and gases, and good self-cleaning properties. The encapsulant. This is used to provide adhesion between the solar cells, the front surface, and the rear side of the module. It must be waterproof and resistant to thermal fatigue and abrasion. The material most widely used is EVA, that is ethylene vinyl acetate. The back cover. This must be waterproof and have low thermal resistance. A film of Tedlar placed on the entire surface of the module is common, although there are also models that use a layer of EVA and a second rear glass. Solar cells and their connectors. Electrical interconnection bus bars tend to be made of stainless steel or aluminium, and they are soldered redundantly with two parallel conductors to increase the collection of carriers on both sides of the cell. Mono and multicrystalline modules are the most abundant type on the market, with typical efficiencies of 13 to 16%. Since they come from ingots, silicon M cells have a semi-square shape, while poly and multicrystalline silicon, since it is crystallized by directional solidification, have a square aspect. There are other technologies that have been developed at an industrial level for the growth of sheets of silicon. These are edge-defined film-fed growth and the string ribbon method. The material obtained with these methods is almost monocrystalline, with electrical properties similar to those of the multicrystalline type. High-efficiency modules are the result of research into these technologies with commercial maturity. In this context, we have photovoltaic modules with back contact cells, in which the front contact is removed, moving to points of contact at the back, and heterojunction with intrinsic thin layer modules, in which the solar cell is made of a thin monocrystalline wafer surrounded by ultra-thin amorphous silicon layers. Thin film technologies are characterized by the deposition of large areas of thin films of conductors and semiconductors on a suitable substrate. Within this group, we have amorphous silicon modules with efficiencies of 5 to 6% in their traditional version and 7 to 8% in the case of modules with multiple joints. They have the advantages of low cost, less use of material and versatility, but the drawback of initial degradation. There are also cadmium telluride modules with slightly higher yields, that is, between 9 and 11%. These are widely present on the market. CIS modules are usually obtained by spraying copper and indium diselenide on sheets of glass. Also developed at commercial level, they afford module efficiencies between 11 and 13%. Associations of photovoltaic cells. Here we see the characteristic curve of a photovoltaic module. A photovoltaic module is a series parallel connection of photovoltaic cells. Its characteristic curve is therefore the equivalent of the cells, but with parameters defined for the module. If we take the example of an association of 36 photovoltaic cells, these could be associated with all of them in series, 36 series, with 18 cells in series, connected in parallel with another 18, or 12 cells connected serially in parallel with the other two branches of 12 series. Since the number of cells is the same, the power obtained is the same, and what varies is the way of combining current voltage pairs, giving rise to different short-circuit currents and open-circuit voltages depending on the combination. The main factors that affect the current voltage characteristic of photovoltaic generators are irradiance and temperature. Irradiance mainly affects the current, so in a first approximation it may be considered that the short-circuit current will be proportional to it. Temperature has a major effect on the voltage and power, such that these decrease with increasing temperature. The coefficient alpha expresses the variation in the short-circuit current with temperature. Beta is the variation in the open-circuit voltage with temperature, and gamma is the variation of the maximum power with temperature. Since the characteristic curve of the photovoltaic module changes with the prevailing environmental conditions, it is necessary to define a set of operating conditions in order to compare the values of different manufacturers and extrapolate information from them to other conditions desired. The most widely used are standard test conditions, or STC. These are the most universal and widespread, and they are defined by irradiance at 1000 watts per meter squared, spectral distribution AM 1.5 G, normal incidence, and a cell temperature of 25 degrees centigrade. Then we have nominal operation conditions, or NOC. These are defined by irradiance at 800 watts per square meter, temperature, which is the nominal operation cell temperature, or NOCT, wind speed at 1 meter per second, and ambient temperature 20 degrees centigrade. Another important descriptor of the photovoltaic module is its efficiency, which can be described in up to 3 different ways, depending on whether it is considered to be the total area of the module, only the portion of the module area covered by cells, or the active part of the cell area. Concentration systems. These are characterized because part of the surface of the cell is replaced by an optical system that is capable of concentrating the amount of incident solar radiation on a smaller cell, providing an electrical production equal to or higher than it would be with cells of equivalent size, but with a lower cost of manufacturing. The relationship between the opening of the collector and the active receiver area is called the geometric concentration, C, and the energetic concentration is the relationship between the incident solar radiation in watts per square meter onto the photovoltaic device and the equivalent irradiance if there were no concentrating elements. Concentration systems can be classified as follows. According to optics, there we have refractive concentrators, reflexive concentrators, and hybrid concentrators, and according to the concentration level. First, low concentration systems. The geometric concentration is 1 less than or equal to x less than or equal to 10. They commonly use conventional silicon cell reflexive elements. Medium concentration systems. The geometric concentration is 10 less than x less than 100. They can also use silicon cells because the concentration rate is not very high. Silicon cells are cheaper than cells from 3,5 compounds. Regarding optics, they can use Fresnel lenses, mirrors, parabolic dishes, and so forth. Finally, we have high concentration systems. The concentration is higher than 100 times, usually with multi-junction cells of 3 to 5 compounds, and in general a point focus. The picture shows images of different types of photovoltaic concentrators. Now let us look at the characterization of solar radiation. According to the direction of propagation that enters the device, solar radiation can be decomposed into beam radiation, diffuse radiation, and reflected radiation. Based on the spectral content of solar radiation, the solar spectrum can be obtained. The main regions or wavelength ranges are the ultraviolet wavelength range, the visible wavelength range, and the infrared wavelength range. Depending on the purpose, solar spectra corresponding to beam, diffuse, and reflected radiation can be considered separately. The extraterrestrial solar spectrum can also be obtained. But now let us look at the geometry of the Sun-Earth system. Basic geometric aspects of the Sun-Earth system are required in order to determine the incident solar radiation in specific areas. First, the latitude of a specific location is determined by the angle formed by the equatorial plane and a line joining that location and the center of the Earth. Second, the declination angle is formed by the equatorial plane of the Earth and the ecliptic, which is the plane described by the Earth's orbit around the Sun. This angle varies from 0 during spring and autumn to 23.45 degrees on the summer and winter solstices. Thus, the maximum solar elevation angle, calculated for a specific location and a specific day of the year, is determined both by the declination angle and the latitude of the location. This latter affects the northern and southern hemispheres in such a way that the summer in the southern hemisphere coincides with the winter in the northern hemisphere and vice versa. For a specific location, the azimuth varies throughout the day at a rate of 15 degrees per hour. The azimuth is equal to 0 at noon, shows a negative value during mornings, and has a positive value during the afternoons. Similarly, at a given moment of the day, two sites that have the same latitude, but whose lengths are separated from each other by 15 degrees, will have a time difference, i.e. local solar time, equal to 1 hour. Influence of the atmosphere. In addition to the geometric parameters, the incident solar radiation is affected by several climatic circumstances. The main ones are characterized by the following parameters. The clearness index is an experimental parameter that relates the daily irradiation on surface directly to the extraterrestrial daily irradiation inferred through geometric factors. The relative air mass factor represents the physical path followed by solar light through the atmosphere. It is referred to as the minimum path. The optical thickness represents the optical path. The optical path is calculated by multiplying the thickness of the atmosphere and its refractive index. The turbidity factor represents the status of the atmosphere for the transmission of light in the absence of clouds. Hence, beam solar radiation is finally calculated from the elevation angle, the air mass factor, optical thickness, and the turbidity factor. Experimental measurements of the clearness index include the similarity between the theoretical expected values and the real ones. Mounting structures and energy generated. The supporting structure of photovoltaic arrays is an important auxiliary element since it covers three fundamental functions. It acts as a frame, conferring rigidity to the assembly of photovoltaic modules, adapting the geometry and layout of the modules. It places modules in their proper orientation and tilt, which will depend on the geographic location in which they are placed and also on the type of application. And finally, it serves as an intermediate element to join the photovoltaic modules with the ground or the construction element to which they are fixed. These could be roofs, walls, etc. They can be either fixed or endowed with solar tracking. Tracking systems are used to achieve a better use of the sun's energy. The most widely used are, first, single horizontal axis tracking systems. The surface rotates about a horizontal axis oriented north-south. We have tracking on an azimuth axis. The surface rotates over a vertical axis. The tilted angle of the surface is constant and equal to the latitude. And then we have polar axis tracking systems, two-axis tracking. The area of photovoltaic modules is always facing the sun perpendicularly, which ensures maximum energy capture. The energy generated. The power obtained by photovoltaic generators can be estimated roughly with the equations shown, once the irradiance and temperature data for the locations and conditions of the installations are known. From this, the values are integrated for the period in which the energy is to be quantified, that is, daily, monthly, or yearly. Associations of photovoltaic modules. In real applications, the cells are not identical, primarily due to two factors. First, the manufacturing process, and second, the operation conditions are not identical. There could be shadowing or clouds, etc. This causes a reduction in the maximum generator power. Moreover, in certain cases, some cells can become loads, dissipating the energy generated by the others. If the dissipated power has a high value, the cell could increase its temperature considerably, leading to deterioration. This phenomenon is known as the hot spot, and protective vices are used in photovoltaic modules to prevent it. To prevent the effects of mismatch between cells, not identical cells, protection is used. This involves bypass and blocking diodes. Bypass diodes are placed in parallel associations of photovoltaic cells in series. They serve two functions: to limit the number of cells whose energy can be dissipated on a single cell, and they provide an alternate path for current in case of failure or partial shade. Blocking diodes are placed in series with the parallel strings. They serve two functions. They prevent current flows in parallel strings in the daytime, and they prevent battery discharge during the night in systems with a battery. Photovoltaic systems that are not grid connected require energy storage systems that will allow consumption when solar radiation is not present. The most important types of storage systems are water tanks or nickel-cadmium or nickel-iron batteries, although lead-acid batteries are the ones most frequently used. Lead-acid batteries are characterized by an operating temperature of -10 to 50 degrees centigrade, an energy density between 10 watts per hour per kilo and 30 watts per hour per kilo, a number of cycles from 500 to 2000, a storage capacity of 50 amps per hour to 12,000 amps per hour. The state of charge is the percentage of charge remaining. Its capacity increases with the density of the electrolyte and decreases with temperature. The depth of discharge, or DOD, is the maximum energy that can be extracted without damaging the battery. Batteries degrade due to overload, overdischarge, sulfation, self-discharge, and electrolyte stratification. Charge regulators and maximum power point tracking, MPPT. Charge regulators prevent the overcharging or discharging of batteries. Maximum power point tracking systems seek the maximum power point of the voltage intensity curve, trying to maximize the production of the photovoltaic generator. DC-AC converters. We are talking about direct current and alternating current. Direct current, alternating current converters transform direct current from the batteries to alternating current. Converters allow the use of conventional market loads operating in alternating current power. They usually incorporate maximum power tracking, thereby optimizing energy production. Looking at loads, first we have lighting. Lighting is one of the most important applications of photovoltaic solar energy. The main applications for lighting with photovoltaic devices are solar lanterns, single-family solar home systems, or SHS, and road and area lighting. They are also used for signaling for land and sea. Water pumping. Another important application of photovoltaic solar energy is water pumping, which supplies water for human and animal consumption and the irrigation of crops. Previous study is required prior to exploitation of aquifers. The pumping system itself consists of a motor and a pump and can be used with direct current or alternating current motors. There are two main types of pumps: positive displacement pumps, which provide a smaller flow of water at a higher pressure, and centrifugal pumps, which supply a greater flow at a lower pressure. Water pumps can be positioned submerged, floating, or near the water surface. Refrigeration. This application is very important for the preservation of vaccines and other medical uses. The system has to be cheap, reliable, and with minimal maintenance. The temperatures required range from 0 to 8 degrees to freeze and to refrigerate. The capacity of the refrigerator is usually between 4 and 200 liters. Other loads and uses. Photovoltaic solar energy can be used for cathodic protection, telecommunications, signaling, and in consumer products. Let us move on to standards. Standardization and accreditation. Standardization and accreditation are important tasks in the field of photovoltaics and include the following activities. Development of standards. The IEC develops world standards. The CENELEC does so in Europe, and AENOR attends to these issues in Spain. Accreditation of laboratories comes from ENAC in Spain. Photovoltaic standards. The main rules affecting solar photovoltaics are: for current voltage curves, the IEC 60904, electrical and climatic characteristics of crystalline generators; IEC 61215 and IEC 61345 for ultraviolet resistance; for thin film technologies, IEC 61646 and IEC 62108 for concentration systems. The safety standard is IEC 61730, and for monitoring and data exchange, it is IEC 61724. For all other system components, BOS, there are IEC 62093 and IEC 62509 for regulators, and for power conditioning and performance that we have IEC 61683. The main standard for autonomous system is IEC 62124, and for pumping systems IEC 61700 and IEC 62253. Finally, for photovoltaic plants, there are the following: IEC 61727, IEC 61929, and IEC 62446. This figure shows the major components of an autonomous photovoltaic system. Except for the solar generator, not all of these components necessarily appear in a given system. Typically, we will find a charge controller and a battery and perhaps an inverter. In the figure, the load lamps are exemplified by the direct current, and for the case of systems including an inverter, alternating current lamps. This table presents a classification of autonomous photovoltaic systems according to their daily energy consumption, which begins at less than 25 watt-hours per day for solar lanterns and above 450 watt-hours per day in community systems. Let us now look at solar home systems and lighting kits. One of the main types of standalone photovoltaic systems are called solar home systems, which provide solar electricity for homes. The lighting kits are solar home systems sold with identical components. So should we look for solar home systems or mini-grids? This figure shows a scheme of two typical kinds of photovoltaic system in the form of mini-grid or solar home systems. They are community or small family systems respectively. Let us look first at solar home systems. Solar home systems are characterized by the following. They require a certain initial investment, perhaps external financing or loans. They have the advantage of being modular and expandable. They do not have large distribution systems, energy counters, administrative expenses, or the possibility of pirated connections. Finally, system failure affects only one home. Moving on to mini-grids. Mini-grids are characterized by the following features. If the houses are close, investment is lower than in equivalent solar home systems. Maintenance and repair are more expensive than in solar home systems. The surplus energy can be distributed, although consumption grows with time. It makes the installation of community services easy. Some faults can be addressed better than in solar home systems, and if there is total failure, this affects many users. Concepts of sizing, Part 1. The design of a photovoltaic system is a selection of the system's components, their relationships, and their position in the system. Sizing consists of choosing the size of the system components in order to supply the service under the conditions specified. The energy consumed can be calculated based on the consumption of direct and alternating current loads and the efficiency of the regulator, inverter, and battery. Battery size is calculated based on the number of days of autonomy, the depth of discharge of the battery, losses in cables and switches, etc., and the nominal battery voltage. Concepts of sizing, Part 2. An important concept is dimensioned peak sun hours, or PSH, representing the average number of hours per day on a horizontal surface at an irradiance of 1,000 watts per square meter. With the relationship between the peak sun hours and consumption, it is possible to estimate the optimal size and orientation of the generator, taking the maximum value for each slope and the minimum of the above values. The result is a tilt that provides the energy needed to the lowest peak power in the worst month. Advanced sizing uses the concept of probability of loss of load probability, LLP. Now let us move on to yields and losses in grid-connected photovoltaic systems. The efficiency of a photovoltaic power plant is analyzed by determining several types of ratios and losses of power. The array yield and final yield ratios stand for the produced and the amounts of energy delivered, respectively. The reference yield parameter stands for the equivalent number of hours of sunlight during a specific period of time. Performance ratio refers to the relationship between the final yield and the reference yield. It is also possible to calculate the temperature-corrected performance ratio, which subtracts the temperature losses. DC power losses account for both the electrical losses produced by the Joule effect in cabling and connections and the thermal losses produced by the heating of photovoltaic modules. Finally, conversion losses refer to the relationship between the amount of energy produced and that delivered. Sizing of grid-connected photovoltaic systems. The following criteria should be used in order to properly size a grid-connected photovoltaic system. Concerning the sizing of the generator system, the working voltage should be maximized to the limit recommended by the manufacturers in order to minimize electrical currents and hence electrical losses for a given value of generated power. In addition, direct current alternating current inverters should offer a high performance level even at lower power rates. Higher nominal power inverters should also be considered for sunny climates. Finally, inverters should admit a wide range of input voltages, and they should adapt the working voltage properly in case of overloads. The sizing of electric wires must consider the admissible voltage losses depending on their length, and also the admissible temperature values in cases of short circuits. Let us look at large photovoltaic power plants. Large photovoltaic power plants are usually installed on uncultivated land far away from big cities. They can also harvest the sun's resource in a better way because they can incorporate tracking or concentration mechanisms. At the same time, large photovoltaic power plants contribute to reducing the unit cost of energy. Let us look now at building integrated photovoltaic systems. Building integrated photovoltaic systems usually take advantage of free areas on urban locations such as roofs and terraces. These kinds of systems help to minimize transportation costs and consumption bills. And we now end with operation and maintenance, monitoring. The operation and maintenance of grid-connected photovoltaic power plants are now characterized by an increasing level of information technology based on the use of automatically controlled devices and the continuous recording of climatic, electrical, and thermal parameters. Data transmission and basic data mining are often performed automatically.